Okay, this is a study paper. I can see from some Fisher Express already, oh, study paper. I know this is 2 o'clock in the afternoon, and I try not to make this presentation completely boring. Okay, so we try to revisit the traditional topographic map and try to enhance and enrich the experience with some modern technologies. And we perform a preliminary study to compare the new form of the map versus the traditional flat map, and have some findings, interesting findings. At least we saw that was interesting findings. First, I'm going to start with some background, and then move to the design of the study, and then some of the numerical and quantitative findings. Topographical map has been there for hundreds of years and is really mature visualization techniques, but just look at that. It's just like overwhelming and just totally difficult to read. This is because actually it's representing a 3D structure, a 3D topographical structure living in the 3D world, and we have to compromise it and distort it and smash it into a lower dimensional medium, which is the 2D map. So during the process, a lot of information has been lost, and when we read the map, we have to reconstruct all those geometric and topographical information. And this is taking a lot of cognitive load, even after years of training. So recently, we have the computer technology, which is getting slightly better, but still they are introducing other things, such as the camera position manipulation, which actually introduce a different layer of cognitive effort. So in general, the traditional topographic map is challenging to read. We actually, again, we are branching this into 2 different branches. First, I'm going to talk about from the cartographic perspective, what happened. Actually, in the cartographic world, in the 70s, researchers has done a lot of amazing stuff. They have done a really big coverage study with hundreds of participants, with dozens different kind of visualization techniques, ranging from some really bizarre and ridiculous ones to some really common used ones, such as contour lines and layer tinting. So there, it's excellent knowledge base. And their finding was, yes, it's a confirmation. It's really difficult to read. However, the twist is, with a proper selection of visualization technique, for some particular task, we can significantly reduce the difficulty of reading those topographical maps. For instance, for visibility tasks, which is standing inside the virtual terrain, what is my visibility, like visible region? For this kind of task, which is commonly used in the field excursion, layer tinting is the best choice, which is use different color patterns to represent the height of different region, and using the layer tinting, the readability of the topographical map can be significantly boosted compared to other visualization techniques. On another side of the story, from the computer science perspective, there are some amazing inventions, such as using sand or clay or flexible fabric with mechanical pillars underneath to represent, to demonstrate a interactive dynamic topographic surface in its 3D form. However, from the computer science side, they are actually inventing new interactive interfaces, rather than visiting from the cartographic design pattern. So, interesting things they're happening on both sides. However, recently, another very popular topic is physicality or tangibility, which is use physical entity to stimulate the touch sensation and to provide extra information. extract information from statistic charts. They print out into a 3D form, so you can actually touch the structure and use head rotation to view it from different angles. Or like traditional visualization techniques with touchable entities and real tangible gadgets, right? You probably all have experience with, like, nowadays with those cars, the central dashboard, they always use fancy touch screens. Probably European cars are slightly better, but North American cars, like, it's going crazy the direction. They use cheap-looking, non-responsive, huge touch screens, and they claim this is cutting edge. This is a trend, but when you're driving, it's just, oh, I don't want to touch the touch screen to control some functionalities. And people really, coming back and getting into these physical interactions a lot. In the cartographic territory, similar things are also happening. For example, people use sculptures to demonstrate the landscape or the city, so you can just walk around and look from different angles and which leverage your natural perceptions. The real models and those sandbox trainings. So this actually gave us the motivation. Because in the past, computer science people and the topographic, the map designers, they are viewing this from totally different perspective. We're thinking, can we actually merge from both sides and revisit the classic topographic map and see how can we increase its readability with some modern technologies. So this is the original motivation. Then it's the design of study. So translate this into the design. We want to compare physical 3D map, which is the scaled representation of the real terrain versus the traditional flat 2D maps. However, we want to add interaction into this because if we want to compare with maps from 70s, it's totally biased and totally unfair. So we want to introduce interactions, dynamic interaction into both 3D map and 2D map with real-time finger tracking. On a 2D map, it will be easy because we can just grab one of those touch screens. But for the 3D map, we actually print out the map into a 3D model and mount a monitor and a projector on the tripod to try to mimicking an equivalent experience of the real-time finger tracking. And we cannot test all the traditional topographical tasks, so we just choose a small aspect, which is the visibility tasks. Remember, I mentioned before, for the traditional flat map, for the visibility tasks, layer tinting was the best choice. So in this way, we actually limited the only variable is the different representation of the height, the elevation. In the 2D map, which is the layer tinting, use a different color pattern to demonstrate the height of individual locations. In the 3D map, we no longer need such visualization because we have the real 3D structure in a solid plastic form already. So that's the only variable difference. The interaction, we're adding a dynamic interactive viewshed, which is this is a common tool for visibility tasks. It tracks the finger and highlight the visible vision from that particular location on the map, situated in the map. On a 2D map, it will be just a rendering of the region. On the 3D map, we use the projector to cast the region onto the 3D model, try to create a similar experience versus the 2D map. So when we translate the design into the implementation, it looks like this. It's really preliminary prototyping. We just use a color sticker to track the finger on the top. There's a camera on the tripod, and based on the location of the camera, the fingertip, we cast the visible region on the physical model, the terrain model. On the 2D map, we use a Microsoft surface and render like a pattern. You see that yellowish mesh, which is the visible region from the exact point of the fingertip. Note that the 3D map is slightly bigger than the 2D map. This is because we cannot achieve the exact, with our prototyping capability, we cannot achieve the exactly same level of the precision and the experience as a really mature technology, which is the touch screen. So we choose to have a slightly bigger 3D map, so people who think the experience is similar. So in the study, we have 4 different conditions, different maps, 2D versus 3D, and each of them with or without the dynamic view shade. So we have 2 different kind of tasks, visibility tasks. The first one is line of sight, which is given 2 points in the map, on the map, can they see each other? Okay. So on the 2D map, it's just like 2 dots with or without the dynamic view shade. On the 3D map, 2 dots with or without the view shade. The second kind of task is the lowest visible point. At any particular point on the map, can this particular person see another dot rendered on the map or not? So on the 2D map, with or without the dynamic shade, the view shade, and on the 3D map. Sorry. Okay. Once again, sorry about that. So the lowest visible point is given 1 point on the map, and we ask the user to find the lowest point which is still inside the visible region. Okay. So on the 2D map, they can select by tap on the screen, and on the 3D map, they can drive this dynamic view shade and select the lowest visible point from a different point. So there are 2 different tasks. 2 tasks, 4 conditions, and we repeat it 5 times. So for each person, we have 40 trials. And we have 20 participants, and we collect the numerical data during the process and the quantitative questionnaires. Actually, it ended up into some free-form discussions with the participants. And we think we collect some really interesting quantitative data, which we didn't expect at all. So the findings. The charts, no, we don't want to do that. I don't want to bore you with all those details, charts, and numbers. Actually, let me jump into the conclusion. So from the numerical finding, okay, people really like the 3D map. Like touching the 3D map actually make it really fun, and I can see most of them, they really enjoy playing with the 3D map. And the 3D map plus the dynamic view shade really boost up the accuracy, especially in those complicated tasks such as the finding the lowest point from a given point. Using 3D map with the dynamic view shade actually really increase the accuracy significantly. However, on another side, we didn't expect it at all. 3D map or dynamic view shade actually reduce the performance. People spend longer time with 3D map or the dynamic view shade, or both of them. And I'm going to justify it later in the later slides. Moving to the quantitative findings, there's something like we didn't expect at all and really interested us. First, people really prefer the 3D map rather than the 2D map. When they were using the 2D map, I can see most of them just give up in the middle of the process. Like, why am I doing this? Using the 2D topographic map, especially with those complicated tasks, well, for $20. But besides that, they're still frustrated using the 2D map. When they move to the 3D map, like most of them really like the idea. I can see not only from their facial expression, like how focused they were during the tasks, but also they constantly touch the 3D model. So I can think that's reflect the nature. They really like the idea. And they are willing to spend more time, just explore the 3D map. And we think this is actually the cause why actually the performance reduced when we move into the 3D map and the viewshed, because they're actually spending more time playing with the toy and kind of like forgot about, okay, this is inside a experiment. So one example is, this is one participant actually draw a chart, like a reference cheat sheet for herself when she was dealing with the 2D map. So she had to constantly moving back and forth between this spectrum of colors and the real 2D map and try to understand what each color represents for. So it was really a torture actually. The second finding was actually people using their dominant hand when they are searching, like navigate on the 3D map. They're using their dominant hand to do the tracking, while they're using their secondary hand to do like temporary location storage. Okay, this can be a candidate of the lowest point, and they put another finger on top of it, like a placeholder, and then move to a different region. Okay, this can be another candidate, but I'm not really sure which one is lower. They put another finger on top of it. So most of them end up like doing this, a lot of hand dancing on the 3D map. So we thought it's really interesting. Not only they're using the finger to temporarily store the location, but also later on, they can use the really sensitive touch sensation to compare between those fingers, and give them the final conclusion, which location is actually lower than others. And this one we didn't expect at all. Like some of them, like almost half of them, because the way we implement our system, we have the projector and the sensor, the video camera hanging on the top. So driving the dynamic viewshed with hovering is possible. You don't have to literally touch the surface. If it's a touch surface, then you have to constantly touch the surface to interact with the terrain. However, in this case, because we're using the projector, people actually hover above the terrain just a little bit, which gives them equivalent quantity of the result while navigate different region of the terrain. I want to point out is this is not contradicted with like the one I mentioned before. They constantly want to touch the surface. They only use the hovering when driving the dynamic viewshed during the real interaction. Other times they just land their hand on the model. So we think this is because the fluctuation, the irregular surface of the 3D map actually create not even a distribute drag when interacted with the surface. So some of them they don't really like it. So instead they're just hovering to regain the smoothness of the interaction. Another thing is the visual occlusion. Not only the visual occlusion, but also the physical occlusion becomes a huge problem during the process. Not only the geographic structure itself can hide something behind, making it no longer visually accessible, but also fingers or a pointer device, in this case like a pen, can create visual occlusion. On another side, the physical occlusion also is a big issue. For instance, the terrain we chose was not really dramatic. It's kind of flat, so you can literally touch each region, every single point on the model. But imagine a more dramatic terrain with a super deep canyon or a trench, then maybe sometimes use your finger is no longer possible to physically access some particular point on the map. So this can be a big issue. So based on our findings, we have 3 design guidelines for the 3D cartographic design. The first one is just try to embrace the idea of using 3D models. People just like it. People like to touch it. People like to the direct, tangible input from their fingers, and they just love it. If you have a chance, try to use the 3D map. The second is try to be aware of all the alternative methods they can interact with the map. For instance, we didn't expect the hovering at all, but it ended up with half of the participants was actually hovering during interaction. So be prepared, and you might be encountered with some really interesting or really bizarre interaction methods. The third is try to try to think about a way to reduce the casualty caused by the physical inaccessibility, right? So if something is really deep and you cannot reach, either rescale them, make the map flatter, or maybe give them a much sharper pointing device. So in order to avoid physical inaccessibility. So that's all the guidelines we learned from the findings. Limitation and future work. First, the map size. We only study the almost like hand-sized maps. We assume if the maps get bigger, those guidelines will be no longer valid, and they might be a totally different system. For instance, a huge topographic, like 3D topographic map like this, my son is just for the scale for exactly 1 meter at the time when the picture was taken. So the experience and expectation will be dramatically different. Second is the complexity of the terrain. The terrain, the map we choose was kind of flat, so there was not a lot of like physical inaccessibility, but different region of the map will have different solutions. The third one is audience. The 20 participants, they are all general public. They are all university students. They don't really have really deep topographic map experience. So maybe next time we're going to try some domain experts, maybe in the industry or oil and gas field. Maybe next time we can try different common tasks or maybe more interaction techniques. And we want to improve the way we construct and implement our prototype with higher accuracy and positions. So that was it. Any questions? Like, this is a very preliminary study, and we actually want to step out away from the traditional computer science perspective and try to view the interaction from the cartographic perspective. So this is really a small aspect, small scope of the infinitely huge area, but if we can set up the stage and inspire some future studies, we will be more than happy. Thank you so much.
Hi, thanks, really interesting talk. I'm wondering, what do you think, so if I'm looking at a topographical map, right, I can in theory, for example, just see the highest and the lowest point just from looking at it, right, for example. And I'm wondering, do you think that because you just used a completely white map, that the only like feedback that you immediately got about the height, if you don't touch it just by looking at it, right, would just be created through possible shadows, for example, that just somehow were generated. Do you think that if you would have projected, like you showed in the 2D map, if you would have projected the same information onto the map as well, that you would have gotten different results?
Excellent question. Actually, yes, I think a combination of the new, like the tangible 3D map. On the top of that, if we add the traditional visualization on the top of that, definitely it will provide more information. Yes, for the simplicity of the comparison, in this case, like we choose to use a planned, like naked 3D map. In this case, it's only for the purpose of the design of the study. But I believe a properly designed combination, the 2D visualization and the 3D physicality, definitely can boost up the readability of the map. However, there's a trade-off. Like, remember the traditional 2D topographic map, one really significant issue was the information density. It's overwhelming already. It's like overloaded, a lot of things going on in the map already, right? So maybe using the 3D map, we can reduce the visualization, the information density in the visualization, right? If you add back those 2D rendering on the top, maybe do this selectively, right? Rather than we just recasting, just print everything on top of the 3D map. So I think that there will be, like, further study will be required for this kind of like detailed tweak. But in general, I think a combination will be really helpful.
So I think this is cool work. I'm really struggling to find the sort of the practical use case where you've got a computer available to you, but it can't just solve the problem for you in this particular case.
Okay. Well, it's actually the cost of the 3D map actually is one of the biggest challenge at this moment, right? So, like, try to imagine in the future, in a real field excursion, right? Instead of carrying a whole bunch of the 2D map, if we can have a 3D printer carry it with us and just keep printing out 3D maps, of course they need to be eco-friendly, right? They can be just thrown away any moment. But if the cost of doing such a thing will be low enough, like, what's your choice, right? Of course, for a domain expert, for people who's really familiar with reading those maps, maybe the benefit is really minimum. But think about if this is an educational session or a training session, then maybe the benefit will be more significant. Next, sorry, just like one step ahead, right? The final vision will be if one day the 2D map, there's no boundary between 2D map and 3D map. If they can merge together, imagine in the future, the surface of your touch screen of your cell phone is shape-shifting. Right? They can bump up, they can create it into any kind of geometric shape, probably not like floating surface on a sphere on the top, but at least for topographic map, it's possible, right? Just elevate different pixels into different height, right? At that step, there's no difference between the traditional topographic map and the 3D model. You can still use your nature, the touch experience while you're still receiving the tangible feedback. So that's the long-term version.
Thank you.
Did that answer your question?
It did, actually.
Thank you.
Thank you.